Anyone have anything?
Resonance.
Does it have to do with the thermodynamics, like the free energy exchange?
Not exactly. So it has to do with just if you have a carbon. So I guess, yeah, we were having this.
Oops.
That was loud.
Sorry.
No worries. So I guess if we talk about it this way. Then if we have. So we have 5 different types of radicals. So it's not necessarily about them reacting. It does determine reactivity, but it's more just if you have a radical sitting on a carbon molecule, depending on the type of carbon that it sits on, will determine how stable it is. So that's just a truth. So basically, we have a methyl, and then a primary, secondary, tertiary, and then resonated radical. So do you guys kind of understand what I mean when I say those terms?
Yeah.
Yeah?
Yeah.
All right. So based off of, so if I draw these, this is what I talk about when I say radical stability. What do you think is the most stable?
The methyl.
You say the methyl?
Yeah.
So why do you say that?
Because it's smaller. Oh, I don't know, actually. Because the radical is just attached to one carbon.
So what exactly is a radical in general?
Like a single electron, right?
So yeah, we can think of it as an unpaired electron.
Yeah.
Right. So if we have this one is unpaired. So I was talking about this with Daniel yesterday. So if we were to compare this to a carbocation and an anion, which one is the radical more like in nature? So I guess what's the nature of a carbocation?
I don't understand.
So I guess, so what characterizes, in terms of orbitals and electrons filling them, what characterizes a carbocation? Is it electron deficient, or does it have a surplus of electrons?
It's electron deficient.
Yeah, so it's electron deficient. It has an empty orbital,
right?
Basically. And then if we have this guy over here, is this one electron deficient or electron, I guess, sufficient?
Electron sufficient.
Yeah. Well, yeah. It has too many electrons, but it's the opposite of a carbocation.
Right.
So I guess the question is a radical more like a carbocation in the sense that it's electron deficient, or is it more like a carbanion where it has a surplus of electrons?
More like a carbocation, right?
So why do you say that?
Because it's missing an electron.
Rosa,
what?
Oh, I was so that's a good response. But I'm asking Rosa. Rosa, what do you think? Rosa?
To be honest.
You're not
I was
sure?
looking at my notes.
Oh, okay.
Yeah, sorry.
But
what did you ask?
So the question is a radical more like a carbocation or a carbanion? So the question is really, is a radical carbon deficient or does it have a surplus of electrons?
I would say it's more carbocation.
Okay, so two people say it's carbocation, and then Daniel and I reviewed this yesterday, so don't worry, we'll go over stuff we didn't review. So yeah, you guys are both right. It's more like a carbocation in the sense that it's electron deficient. So it actually, a radical doesn't have a charge. It's kind of a weird thing, but we can always think of it as having one less electron than it needs to have. So it's a little bit more like a carbocation because it lacks electron density. So if we have something that lacks electrons, lacks the necessary amount of electrons that it wants, then what do you think that needs? What do you think it wants?
It wants to gain an electron, right? Or get rid of the radical.
Yeah, so it wants to either gain one electron, like you said, or get rid of the radical because radicals are just super, super reactive, but that's for other reasons. Or there's actually something else. So if something, it doesn't necessarily have to gain another electron to gain stability. It can just gain electron density, which is a little bit distinct. It's basically the idea that it's not necessarily that there's another electron in that orbital. There's just electrons around that orbital that can kind of help alleviate the pain of not having that extra electron. Does that kind of make sense?
Yes.
Yeah? Okay. So thinking about that now, what we're talking about when we're talking about radical stability is we're talking about either delocalizing the radical or we're talking about giving that radical electron density. So thinking about that now, do you think that the methyl radical is more or less stable than everything else?
Less.
So Rose says less. Scythe, what do you say?
I think he said he's gonna be right back.
Okay. That would have been really awkward. And then Daniel, what do you say?
Yep.
Okay. So we have 2 for yes and 1 is gone. So less stable. So what if we jumped over to this guy right here? What kind of carbon, what kind of radical is this? Is this a primary, secondary, tertiary?
Secondary.
So Daniel says secondary, Rosa says yes. So is that more or less stable compared to the stuff on the right of it?
More stable.
So compared to this stuff?
Mm-hmm.
And then what do you say, Daniel?
That is more stable than the methyl, yeah.
Yeah. And then if we jumped over here, then where does this fall in line when it comes to stability?
Which one? The primary?
This one on the very end. So what makes that one on the very end different from the other ones?
Is that one considered like an allylic? Is that how you say it?
Yeah.
Yeah.
That's it. So if it's allylic, what does that mean?
That it's stable?
Yeah, it's more stable. So that's just it's just a truth that resonance stabilizes charges and radicals. So the resonance structure, I don't think I drew any yesterday, so this is good to see. Is going to look like this. So basically the idea is that the trend goes like this. By the way, I'm recording these. I'm planning on putting them on YouTube so I could share them with you guys. Is that okay?
Yeah.
Okay, cool. So I'm gonna, well, I'll probably open up that tab and then review it when Scythe comes back. But so next in the agenda is to do a bromination predicted products question. So this is 4-47. Oh, hey, Scythe.
Hi.
So I'll just show you really quickly. So this is what we were talking about. I wanted to make sure that everyone can kind of see this, even though you weren't involved in the discussion because you had to go somewhere. But so basically the trend is that if you have something that is less substituted as a radical, or this is also true for carbocations actually. If it's less substituted, it's less stable. But if it's more substituted, it's more stable, and then resonance stabilizes everything the most. So the trend. So I'm going to say something really quick. So the trend reverses. So this is true for carbocations and radicals. The trend reverses for carbanions. And then I'll just state really quickly because I want to make sure that we move on to the next part. So the reason why that happens is because of something called hyperconjugation. And hyperconjugation is basically the idea that, so these hydrogens, they're just protons basically. But then, because, I don't know, that's just kind of what hydrogen is. We think of it as a proton and a neutron. Yeah. But then inside of these bonds between a carbon and another carbon, there's 2 electrons. And then there's 2 electrons, 2 electrons. So those bonds between carbons can donate electron density. And so what kind of happens if we have a radical or a carbocation, these guys, so I'm gonna do this with a tertiary because it's easiest to see. These guys will kind of fold over inwards to donate electron density, and that's called hyperconjugation.
Okay, I see.
Yeah. But then, so why do you guys think that that would not stabilize a carbanion? Why does the trend reverse for a carbanion?
Is it because it wants to gain electrons? So it has to do with like the electron density?
So you're saying that the carbanion, so we're talking about this guy. So we're talking about the negative charge. Mm. So the trend reverses for carbanions because, well, I'm not gonna say why actually, not yet. But I guess if we have something like this, this is less stable than this. So why do you think that is based off of what I just said about hyperconjugation?
Would it be because the sort of like sharing of electron. Sorry, the word is escaping me. Like electron density sort of repels other electrons and doesn't allow for bonding.
I think you're around the right idea. So you're saying that there's electron density in these guys, right?
Yeah.
But then there's also electron density on a charge. Is that kind of what you're saying?
I'm saying that the shared electron densities would sort of repel like other electrons that would come in to fill the deficiency wherever the charge is deficient.
I think you're saying the right thing. I think I would word it a little bit differently. But I think that you have the right idea. So the idea is basically that there's so if you have a carbanion, it's electron rich. And if you have those carbon-carbon bonds, those have electron density. And electrons like repels like. So if you have a lot of electron density and you have something that's electron rich, then that means that they don't want to be near each other.
Okay. Right.
So give me a second, actually. Ah, shoot. So is that good with everyone?
Yeah.
Okay. Cool. So let's move on to some predict the product questions. So again, this is 4-47 in the book. So I'm going to write these down. And I'm going to have to stop screen share for a quick second after I write them down so I can invite my boss.
Okay.
Is this the first time that you guys have seen these questions? Or did you see them mastering? Or
There were predicting the product questions on mastering. Like they gave you the full equation and you had to draw out the mechanics.
okay. Oh, you had to draw the mechanism?
Yeah, like all the steps.
Okay, cool. Yeah, I know Dr. Tyler didn't really review the actual mechanism. I don't think he'll have it on the quiz, but I could be wrong. So I'll give you guys a moment to write that down, and then I'm gonna have to stop screen share and then invite my boss to the session. Did you guys copy them down?
Yeah, I got them.
All right, cool. Stop share really quick. Wait a second. Is anyone having a hard time with the question?
I'm just trying to find it in my book because I have old. edition.
What was that?
I'm just trying to find it in my book because I have the old edition, the 8th edition.
Okay. Oh, by the way, I think if you guys want to write on the whiteboard, you can, but I think you have to enable it in your options. So if you guys want to do that, that's perfectly fine.
Did something come out on the board?
Yeah. So I guess, did anyone get the answer to A?
Yeah.
Okay. So if you guys want, you can write your answer on the board. Maybe like wait a little bit after you get the first answer, like try to answer as many as you can. And then if no one else has written the answer, then you can write it. If you get it immediately, then just wait a little bit. So that way people can kind of have some time to digest it. But if anyone wants to write their answer, you can. So for that last one, there's 2 different products. And then for this one, there's also 2 products. So for C and E, there's 2 products. Give you guys 1 more minute and then we'll start going over it. Okay. So what did you guys get for A? All right. So what do you guys think of that?
That's what I got.
Yeah.
So it looks like we're all in agreement. So that is good. That's good. So yeah, that's true. So what about the second one? By the way, in about 10 minutes, the meeting is going to cancel because I have a 40-minute time limit because I don't have like the best Zoom account possible. So that video is going to stop, and then I'm going to send out a second video.
Okay.
So we could finish up the last 20 or so minutes.
Something like that.
What do you guys think?
I got something different.
What'd you get?
So mine looks like this. And then I guess there'd be a C here.
So between those two options, what do you guys think is more likely? And then, Scythe, why did you choose that one? And Daniel, why did you choose that one?
I chose that one because the third tertiary carbon is going to replace the hydrogen over there.
So why does it replace that hydrogen as opposed to any other hydrogen?
The other ones are primary and secondary. I remember reading something in my notes about that.
Then what about Scythe? What do you got?
Because it was the end hydrogen.
So why does it being the end hydrogen affect anything?
I don't know.
Was it just kind of a little bit of a guess?
Yeah.
Okay, I mean that's fine as long as you understand it later. So and then Rosa, what do you think?
I got the first one.
All right. So two people have the one on the tertiary and one person has the one on the primary. So it turns out that this one dominates. This one, it might show up, but it would be extremely minor. And you kind of have to go through the mechanism in order to justify this. But so when we were talking about radical stability plays in, basically is the reason why, what the heck? Radical stability is basically the reason why it turns out like this. So if you go through the mechanism, now I'm not going to draw the whole thing, but if you go through the mechanism, you end up forming a radical on the most stable carbon possible, especially for bromination. Bromination is very specific. Bromination will always go for the place where the radical is most stable. Does that kind of make sense?
Yeah.
So the radical is the most stable right here. And so in the mechanism, you're going to have a radical that forms right there, kind of like this. And I mean, it's perfectly fine that you didn't get it right. It's just that you have to make sure that you correct it. So,
Yeah.
you know, now is the time to be wrong, not on the exam. So, does everyone kind of get that?
Yeah.
So that's just kind of the trend. You have to look at the stability trends in the previous problem in order to determine what the result will be. So what about C?
Oh god, that's so ugly.
I very briefly saw that and I was like, what the? That's fine.
Something like this.
So that's good. So that's definitely one of the products. And then so the book says that there's two different products. So what's that other product, do you think?
Mm. Would it just be on the other side?
Like right here?
Yeah, something like that, yeah.
What do you guys think?
Yeah.
Then Rosa, what do you think?
Yeah.
I mean, like all the ones in the middle are secondary, right?
Secondary, yeah.
Yeah,
And
so
then,
this guy, this guy, this guy, and this guy.
yeah.
They're all possible candidates, right? But then these guys suck. They're terrible. So these guys, so the terminal carbons aren't going to show up they're not going to be brominated, but it's possible for any of these other ones to be brominated. So there's actually a specific other carbon that it goes to. So you said that it could go here?
It can also go to the primary carbon, right?
To these ones?
Yeah.
It would be a minor product, a very minor product.
Mm.
So I guess between this one and this one, which one do you think it'll go for?
The one on top, I would say.
So why do you say the one on top?
Because it's closer into the molecule. Like it's close, it's further from the ends, I guess.
So I think there might be some argument for that. I'm not entirely sure. But actually turns out that you're right, it is this one. But the reason is a little bit different. And the reason actually has to do with, so if I drew this guy. So we already drew one. Oh, wait. Oh, you said that. Oh, wait, never mind. I'm sorry. I got it wrong. It's not this guy, it's the other one. So we drew one with the bromine right here. So if I drew another, oh, dang it. Give me a second. So if I drew another one with the bromine right here, is that the same molecule or is that a different molecule?
If you just like flip it around, it's the same
Yeah.
molecule.
Yeah, so if you flip it around, it's the same one.
Okay.
And so that's the reason why.
I
So
see.
it's basically, so there's two identical carbons that you could brominate, and they're going to lead to the same product. And so that's true. So this guy's identical with this guy's identical with this guy, and this guy's identical with this guy.
Okay.
So it leads to the same product. So it will brominate there. It just doesn't matter because we already have the answer. What about the other carbon? So what's the other possibility? Between 1 and 2.
Would be this one.
You see that one?
Yeah.
So the meeting's about to pause, and then I'm gonna have to send out another thing. But yeah, it would be that one.
Okay.
Yeah, it says less than a minute until we go on. So